Wonderful. So welcome to the propagation stage of the foundation license. This is quite a short one. So we'll make a move. What's going on? Right. Can you all still see that?
Yes.
Yeah.
Wonderful. Right. So we're going to look this time at radio waves. We're going to look at the ionosphere and the effects that the ionosphere has on HF and VHF, UHF, as well as some other little bits and pieces involved with those. So just some bullet points to begin with. Radio waves travel in straight lines, much like light travels in straight lines. It's all part of the electromagnetic spectrum. So it's always a straight line. But again, like light, radio waves can be reflected, refracted, or diffracted, okay, or bent. And we'll go into this a bit more in a bit. They do get weaker as they travel further from the transmitter. Very much like throwing a ball. When it first leaves your hand, it's got a lot of power behind it, but as it travels, the power dissipates and the ball falls to the floor. Now, radio waves don't fall to the floor, but they do sort of dissipate themselves as the power diminishes. The distance that the wave travels does depend on some other factors as well, including the type of antenna you're using. It will go further with, say, a Yagi than it will with a dipole or a 5/8 wave. It depends on the frequency. A low frequency with a longer wavelength will go further than a high frequency with a shorter wavelength, because the lower frequency will have to travel further to complete one cycle than a higher frequency. Again, power, the amount of power you put behind it, and obstructions. If there's something in the way of the radio wave that it won't penetrate, it's not going to go much further than that. And also the conditions of the atmosphere, that plays a part as well. So the ionosphere, that is a layer of conductive gases between 70 and 400 kilometers above the Earth. The ionization is mainly caused by ultraviolet rays from the sun. And so the sun's atmosphere, so to speak, although it's not an atmosphere as such, plays a great deal in how well radio waves on Earth travel. By the ultraviolet rays will change the ionosphere so that some waves will travel really well, others won't travel at all, and vice versa. So we'll go more into that in a minute, but when the radio waves travel well through the ionosphere or off the ionosphere, that is known as the band being open. And when it doesn't, the band is known as closed, and it changes from band to band. So one band could be really good, another band can be not so good. However, VHF and UHF signals pass through the layer. They do not reflect off the ionosphere at all. But HF signals are refracted or bent back down to Earth, as you can see with this diagram. So there's a station here transmitting, it's coming up to the ionosphere, and it's being reflected or refracted back down onto Earth. So talking of refraction, we've got a visual representation of light refraction going on, where we know the straw coming into the glass is straight, but because of the water within the glass, the light coming in is being bent. So we don't see the straw as being straight. HF signals are also refracted off the ionosphere, and this allows us worldwide contacts that go far beyond the line of sight. The HF bands are open. For example, they support the skywave propagation that's going on at different times of the day and different times of the year. And each HF band is affected differently. As you go through some websites, you'll see this little almost weather report appear. Lots of amateurs have them on their websites. They're also on some of the more official websites, and it just tells you how well each band is going to perform during that 24-hour period. Some of these can get a little bit more complicated than just this, but this is quite a basic one. Solar activity has a big effect on our ionosphere, and contact around the world is done using multiple hops. So if we have a station over here on the planet and they transmit and their signal goes up here, it will be refracted back down and back up and back down. Okay, so that's what allows you to get quite far. Yeah. With VHF and UHF, the range of these two bands is less than that of HF. It's typically limited to just be on the line of sight. The range decreases as the frequency increases. So if you're looking at low band VHF, those signals are going to travel further than a UHF transmission, because the frequency in UHF is that much higher. So the range decreases as the frequency increases. At VHF, UHF frequencies, radio waves also get weaker when penetrating buildings. Glass is more transparent to radio waves. You will find, so where I live, if I've got a handheld and I stand in my, I suppose you would call it a porch, sort of, I will not receive anything on my handheld, even with the door open. But the moment I step out of the door, my radio will light up with signals. The building really plays a huge part in whether I can receive or not. Snow and ice and heavy rain can also attenuate signals at UHF and above. So attenuation is, for want of this, it reduces the signal quality and the signal power. If you have an attenuator in your radio, it's reducing your power. So those weather conditions can affect the signal. And this can be quite prevalent. If you're having a UHF communication with someone over a period of hours, you will find that whilst it's not raining, it will be a much better quality signal than when it's raining or snowing. That does make one hell of a difference on UHF. It can also be blocked by obstructions, hence antennas are normally located outdoors at high points. As I said, when I'm inside my house, my radio is not particularly good. So if you have a building between yourself and another station or a range of hills, that is going to affect your range whilst transmitting. So hills can also cause shadows. So in this example we've got down here, we've got a whacking great big mountain between two stations. As this station transmits, the waves will shoot over the top, but because radio waves go in a straight line, it will carry on up here, but there'll be nothing down this side of the mountain. So this station down here isn't going to receive anything. There are ways to get around this, but we're not covering that in this presentation, but I'm sure we will later on. So outdoor antennas are preferable to indoor or loft antennas. Excuse me. My current antenna is on a pole in the garden, but it did used to be, where I lived previously, It was in my loft. And actually, I did a lot better there than what I am here, but I was a lot higher up. My house was at the top of a very, very tall hill, and I could get a lot further, even though my antenna was just in the loft. Where it is now, it's a lot lower. Although it's on a mast, it's a lot lower than what it was then. But if I'd had it outside where I was, I could have done even better. So the range of VHF and UHF is dependent on the antenna height. Excuse me. Again, the higher the antenna, the better you're going to do. The antenna gain. It says here using a beam antenna. All antennas will have gain, but if you have a beam antenna, you're putting all the power in one direction. Whereas if you've got a monopole antenna, like a 5/8 wave or something like that, you're going to have less gain than a beam antenna. A clear path. If you've got no hills or anything obstructing, you're going to be able to actually get to where you're trying to transmit to. So a clear path is quite useful. However, the other night when we were on air, we did have a station call in, excuse me, from Bristol and managed to get to us. It was a weak signal, but it did manage to get to us. And your transmitter power. At foundation level, you cannot use more than 10 watts ERP. But you're more likely to get out if you're using the full 10 watts than you are if you're, say, using 5 watts. But if you're only trying to transmit to someone down the road, you may wish to use less power. The higher antennas are, that is more preferable to having high power, as a higher antenna and a good antenna will improve both transmit and receive performance. So the range of VHF and UHF can be extended by some atmospheric conditions as well. We know that VHF and UHF passes through the ionosphere, but propagation can occur through the troposphere, which is below the ionosphere. If you look at the diagram here, we have the ionosphere above, then we have the troposphere, then we have the Earth's surface. So there are two kinds. There is sporadic E and there's atmospheric ducting. These are two ways that these signals can be extended. However, these two ways are also very unpredictable. You will suddenly start to hear signals coming in from, I'd say on 2 meters, you might suddenly hear signals coming in from France and perhaps a bit beyond. And that is normally due to either sporadic E or atmospheric ducting. It happened a few months ago with television signals. There were reports all around the country of people receiving French television. And it was because there was an extended period of atmospheric ducting. We had or sporadic E. We had the same thing happen on amateur radio. It was good fun, actually. We were able to talk to a lot more people from further away. In the amateur world, we do call this a lift. So when there's a lift on, you're going to get signals from further afield. So in summary then, the ionosphere is a layer of conductive gases between 70 and 400 kilometers above the Earth. HF signals travel around the world refracted off the ionosphere. VHF, UHF is generally just beyond the line of sight. And please remember that VHF, UHF, the height of your antenna is more important than the amount of power you use. That is really quite important. The higher you can get your antenna, the better. Do also, though, if you're setting up an antenna, do be aware of planning regulations and things. And if you have any concerns or issues, do feel to contact your local club and that they should be able to help you more. If not, the Radio Society of Great Britain have also got some downloadable pamphlets off their websites that can give you more information on that.